Okay, good afternoon, everybody, and welcome to today's webinar, where we'll be hearing about subsea riser design and the challenges of deepwater oil and gas from Glenn Jewell, who is a senior consultant in the Program and Operations Management Group at Fraser Nash Consultancy based in Surrey. In his role, Glenn supports clients in the offshore oil and gas industry with diverse engineering challenges. He has significant experience in subsea riser engineering, having previously held a senior role at 2H Offshore Engineering Limited. He's led a number of engineering projects considering subsea riser systems and worked with many major operators for deepwater developments at locations around the world. He's a fellow of the IMechE and a chartered manager with the CMI. He graduated from the University of Surrey and still lives locally near Woking. So in a moment, I'll hand over to Glenn, but before I do so, just remind people there will be about 20 minutes for questions and answers at the end of this session after the presentation, but you're welcome to submit questions at any time during the presentation in the chat box provided. And now I'm going to hand over and we can listen to Glenn's presentation.
Hello everybody, and thank you for joining me for today's webinar, titled Subsea Riser Design and the Challenges of Deepwater Oil and Gas. I'm going to provide an overview of the engineering challenges associated with subsea riser design, with particular focus on deepwater oil and gas. I imagine that we have a mixture of experience levels in today's audience. I hope that if you are new to the offshore industry, then this will help you understand what is meant by a subsea riser and the scale of some of the engineering challenges. If you are already working in this industry, then perhaps this presentation will shed a little more light on the specific challenges of riser design. The offshore industry is not new. We have been extracting hydrocarbons from subsea reservoirs for many decades. However, offshore production is now moving into ever deeper water and increasingly harsh environments. The hydrocarbons are brought from beneath the seabed to the sea surface inside a pipeline that is known as a subsea riser. The riser is used to transport various fluids and also equipment between the seabed and the surface. This sounds straightforward, but as I will show you, there are many complex engineering challenges that must be safely overcome. Offshore oil and gas is an important part of our everyday lives. For example, most people would see a petrol station and recognize that the fuel is ultimately derived from hydrocarbons that are extracted from underground. I expect that many people would recognize this as an offshore oil rig, although this is often the limit of their knowledge. Outside of the industry, few people would be aware of what is happening beneath the surface. I certainly knew nothing about subsea engineering when I graduated and entered the industry. Those of you working in the offshore industry might also look at this image and think it has been taken on a day with particularly fine weather, especially for the UK North Sea where this rig is located. It certainly isn't always this pleasant. This image is more representative of the harsh environments we must consider. The Braga platform, shown here, is located 125 kilometres west of Bergen in the Norwegian North Sea, in a water depth of 137 metres. This rig has been producing oil since 1993. As we strip away the harsh environment at the sea surface, we see a new world of complexities beneath the surface. This particular example is the Shell Gumusut platform, which has been operating offshore Malaysia since 2014, in a water depth of 1,200 metres. Each of the coloured lines represents a separate riser. As you can see, the risers may be transporting oil, gas or water, and there are also umbilicals used to control equipment at the seabed. There will be different design requirements depending on the fluid content of each riser, and their dynamic response will vary as a result. But this is just one example, and the subsea risers will be different in every field. The graphic shown here does not represent a single field, but is a schematic to illustrate the various forms that may be taken by subsea risers. As I will explain, each field location has its own unique requirements. In relatively shallow water, a fixed platform can be used, where the structure is installed directly onto the seabed. This is shown on the left-hand side. In deeper water, a fixed platform is no longer possible and a floating vessel is required. This can take various forms, ranging from a ship-shaped vessel to something more recognizable as an oil rig. The risers themselves can also take different forms, and if you look closely, you may see that the risers in this schematic vary. Some are vertical, some are in a catenary shape, and others are in a more complex form. More on that later. It's worth briefly reminding ourselves of why we extract hydrocarbons offshore. Hydrocarbons are found in reservoirs located beneath the seabed. However, this is not a reservoir such as that used to store our water. Instead, the hydrocarbons are present in small quantities contained in porosity within the rock. The reservoirs may be several thousand meters below the seabed and spread across a large area. The potential position of such reservoirs can be identified using seismic analysis. Subsequently, exploration drilling is required to confirm the status at the identified location. It's not just about finding hydrocarbons. Extraction is very costly, and the result must be worth the effort. Often, field developments comprise multiple wells to make recovery economic. It's also worth briefly highlighting the importance of directional drilling, which enables wells to be drilled across long distances, including around corners and horizontally. I mentioned earlier that we have been extracting hydrocarbons offshore for many decades. The first offshore wells were drilled in the Gulf of Mexico in shallow water. These early wells used fixed platforms, with structures installed directly above the well. This technology was brought to the UK North Sea in the 1970s and is now common around the world. Fixed platform structures have become increasingly advanced and can be used in water depths of up to around 300 meters. That is roughly the same height as the Eiffel Tower. In greater water depths, it becomes increasingly impractical to have a fixed structure, so floating systems are used. Floating systems can take various forms. Without a structural connection to the seabed, position at the surface is maintained within a given radius by moorings or dynamic positioning. I won't talk through the image shown here in detail, but it is another schematic that shows the various designs of fixed structures and floating vessels that may be used. The design requirements for the Subsea Riser depend heavily on both the water depth and the type of platform used. So, what exactly do we mean by the term deep water? Typically, anything greater than a few hundred meters may be considered as deep water, although there is no fixed definition for the term. To put things into perspective, I like to compare with structures we are familiar with on dry land. Many of you will know of the Burj Khalifa Tower in Dubai. At a height of 830 meters, it is the tallest building in the world. There are 163 floors, with the top floor at 585 meters above ground level. I think we can agree it is a hugely impressive structure and a fantastic engineering achievement. But it pales into insignificance compared to the depths to which we install subsea risers. We now routinely operate in water depths exceeding 2,000 meters, with the deepest wells in water depths exceeding 3,000 meters. I admit the riser pipe is not a structure of the same complexity as a skyscraper, but there are a unique set of engineering challenges for a deep water subsea riser, which perhaps makes the achievement worthy of comparison. Subsea risers can be broadly split into two categories: exploration and production. Exploration risers are used in the early stages of a well development. At this stage, a potential source will have been identified through seismic analysis, but it is required to drill a physical well to confirm exactly what is to be found at the given location. Exploration makes use of specialist drilling vessels that move between well locations. The drilling equipment is lowered to the seabed through a drilling riser. This is standardized existing equipment, and hence the configuration of the drilling riser must be optimized to suit a particular location. Analysis is performed to determine safe operating limits. An exploration well is typically a short duration campaign, perhaps lasting between 1 and 3 months, with just a single well being drilled at any one time. The exploration phase confirms the reservoir details, testing the predicted hydrocarbon reserves for quantity and quality, and helping to define economic options for further development. If the exploration well is successful, there may be subsequent activity using completion and workover risers to prepare the well for future production operations. The second category of subsea risers is production, including export. The production system may comprise multiple risers, transporting fluids both to and from the surface vessel. Unlike exploration risers, production risers are typically bespoke designs for a particular location. They can take various configurations, including the use of dry or wet trees and the use of rigid or flexible pipe. Production risers often have a target service life of at least 25 years, and it is essential to ensure safe, continuous operation for this duration. The long service life poses a particular challenge, as it is difficult to inspect the riser subsea, and even harder to replace components. Now to look at those two categories of riser system in a little more detail, starting with the drilling riser. A drilling riser typically consists of a number of pipe joints that come with the contracted drilling vessel. These individual pipe joints are made up to form the required riser string. The riser is connected to the wellhead just above the seabed and is connected to a fixed platform or floating vessel at the drill floor. The majority of the riser is made up of 40-foot long joints of steel pipe, which may be slick or buoyant. A slick joint is a conventional steel pipe, while a buoyant joint includes an outer covering of material to reduce its weight in water. The use of buoyancy is often essential to reduce the riser's submerged weight, although there is a trade-off due to the increased hydrodynamic drag. The buoyant joints themselves come in different ratings, suitable for use at different water depths. A number of additional components prevent the riser from being a simple pipeline between seabed and surface. A telescopic joint near the surface allows for total riser length to vary or stroke as the vessel moves around with the effects of waves and currents. At the top and bottom of the riser, flexible joints allow a small amount of rotation, which alleviates the high loads experienced at these locations. Near the riser base, the lower marine riser package, or LMRP, and the blowout preventer, or BOP, are large pieces of equipment that enable well control to be maintained safely. Beneath the wellhead, the conductor and a number of internal casings extend into the seabed. At the riser base, the outermost conductor pipe acts as a structural foundation. This is typically around 30 or 36 inches in diameter. Inside the conductor, several concentric casings are hung from the wellhead. The smallest casing will continue down to the reservoir, potentially several kilometres beneath the seabed. Although the majority of the conductor is located beneath the seabed, this region will still experience loading from the riser, and it is important that we understand and model the interaction between the pipe and the soil. The seabed is not solid, but comprises layers of clay and sand of varying strength and stiffness. The soil parameters are different at each well location. Depending on conditions, the dynamic behavior can extend to around 40 meters beneath the seabed. Now, looking more closely at production risers, I will start with dry tree systems. The reference to trees is due to the location of the Christmas tree. The tree is so called because supposedly it looks a bit like a decorated Christmas tree, although I think you need a lot of imagination to see this. This example shows top tensioned risers, or TTRs, installed from a TLP, that is, a tension leg platform. In a dry tree system, the well pressure barrier is installed on the vessel with the control equipment in an accessible location, either dry or in the splash zone just above the sea surface. With the pressure barrier at the surface, a high pressure riser is used. This means a small diameter pipe, something like 14 inches in diameter, and a high pressure rating. The small pipe size reduces the riser weight, meaning a lower tensioning requirement. And the vertical riser allows direct access into the well where needed. This approach can be suitable for developments with multiple wells or with complex reservoirs. Alternatively, we can consider wet tree production riser systems. As you may have worked out, in a wet tree system, the well pressure barrier and control equipment is installed subsea at the seabed. Direct access to the well is no longer possible, and a separate vessel is required for drilling and workover activities. With the pressure barrier at the seabed, a low pressure riser is used. This means a larger diameter pipe of around 21 inches in diameter. There are various configurations of wet tree production riser systems. The steel catenary riser passes from surface to seabed in a simple catenary shape, ultimately touching down and continuing along the seabed as a horizontal pipeline. This configuration can be developed further into various forms of wave risers, where additional buoyancy, weights, or structures can be used to introduce additional shape to the riser. This shape has the benefit of separating the riser base from the dynamic motions that are inherent near the sea surface, thereby reducing critical extreme and fatigue loading on the riser at the seabed. This concept of dynamic separation is extended further in the hybrid riser. In this system, a vertical rigid pipe is supported by a buoyancy tank some distance below the sea surface. A flexible pipe is then used to connect to the floating vessel. In describing the hybrid riser just now, I used the terms rigid and flexible pipe, so I should explain what these mean. Rigid pipe refers to discrete lengths of steel pipe. Flexible pipe is more complex, consisting of a complex cross-section of steel interlocking or wound layers and polymeric layers. To fully describe the purpose and behavior of each layer could fill another presentation. Of course, a so-called rigid pipe still has a large amount of compliance when considering a pipe length in the hundreds of meters. Equally, a so-called flexible pipe still has a certain amount of stiffness and will not bend freely. However, the difference is relative, with the flexible pipe offering reduced bending stiffness and hence increased capacity to withstand extreme and fatigue loading. As often happens, there is a trade-off in design here, with different systems being more or less suitable for particular applications. The challenges associated with riser design are significant. The weight of the riser pipe may reach several hundred tons, and the riser is a slender, unsupported structure, which makes it vulnerable to buckling. Then we have dynamic loading, which is highly complex. Hydrodynamic loading from waves and currents exert drag forces on the riser. Environmental loading, including wind and waves, also act on the vessel and top of the riser, causing dynamic motions and lateral offsets. The riser structure must withstand both the high extreme stresses and the fatigue damage that can occur due to cyclical loading. Additionally, the riser must be designed to withstand high pressures and variable temperatures, both inside and outside of the pipe. Flow assurance is a key concern. It is essential that the hydrocarbons will flow through the pipe as planned. And on the outer surface of the pipe, marine growth is a consideration, potentially introducing increased weight and drag to the system. We need to select materials that are suitable for the application and consider how the equipment will be fabricated and installed. And all of this while achieving a target design life that may be 20 or 30 years. But the overriding concern is how we can meet these design challenges safely. Any failure can have huge implications in terms of lost production, impact to human life, and pollution. I will briefly discuss a couple of well-known examples to highlight this point. I hope you are all aware of the Piper Alpha disaster. Although this occurred over 30 years ago, it still directly affects how we work in the offshore industry today, and it is important to remember what happened. The Piper Alpha platform began production in the UK North Sea in 1976. The platform was destroyed by an explosion and resulting fire on the 6th of July 1988. The explosion destroyed the control room and prevented access to the lifeboats. Meanwhile, gas continued to be pumped to Piper Alpha from adjacent rigs through two large pipelines. This gas fed the fire and led to further explosions, which destroyed the platform and restricted rescue efforts. 167 people died in the disaster, and there were only 62 survivors. The total insured loss was estimated at around £1.7 billion. There were a number of contributing factors to the disaster, but ultimately it was the removal of a safety valve on a condensate pump for routine maintenance and its replacement with a temporary disc cover that led to the failure. Without effective communication between teams working on different shifts, the out-of-service pump was incorrectly restarted. This led to the gas leak and subsequent explosions. Following the disaster, a large public inquiry was held. In the resulting Cullen report, there were 106 recommendations, all of which were promptly adopted. As a result, safety responsibilities were shared between the regulator and the industry. The responsibility for enforcing safety in the North Sea moved to the Health and Safety Executive, or HSE. Previously, production and safety had both been overseen by the same agency. The key recommendation was to introduce the safety case approach, whereby the operator of every fixed and mobile installation operating in UK waters must submit a safety case to the HSE for approval. This must demonstrate that there are suitable safety management systems in place and risks have been identified and reduced to as low as reasonably practicable, otherwise known as ALARP. Although it was not a riser fault that led to the Piper Alpha disaster, I include it today to show what can happen when things go wrong, and hence the importance of maintaining safe systems as our top priority at all times. More recently, there was the Deepwater Horizon disaster in the Gulf of Mexico. A well was being drilled at the Macondo prospect in 1,600 meters of water. On the 20th of April 2010, high-pressure methane gas from the well expanded into the riser and rose into the drilling rig, where it ignited and exploded. 11 of the crew died in the explosion, with the rig sinking 2 days later. Oil continued to flow from the well for a further 87 days before it could be contained. The total volume of the oil leak is disputed, but is estimated at around 4.9 million barrels, making it the largest marine oil spill in history. The investigation into the disaster found multiple failure points, and there is not time to discuss them all today. Leaving aside some of the more speculative claims of the Hollywood movie, the well construction was inadequate to contain high-pressure oil from the reservoir. For various reasons, it was not detected that there were problems with the well seal, and that pressure readings at the rig were increasing. The design of the mud separation and venting systems allowed gas to move into critical areas of the rig, from where the disaster could not be averted. Additionally, multiple failures of the blowout preventer, or BOP, prevented subsequent sealing of the well, allowing the release of oil to continue unchecked. Extensive engineering was required to resolve the situation, including the use of containment devices and additional risers to collect oil and transfer it to the surface, and the drilling of 2 relief wells to reduce pressure at the damaged well. The cleanup, legal action and compensation claims continued for several years. The 2 previous examples illustrate the scale on which things can go wrong. To prevent such disasters from occurring, a well-established set of industry design codes and standards are used to ensure the riser system is fit for purpose and can be operated safely. I'm not expecting you to be able to read the text on this image, but this illustrates the breadth of design codes as published by ISO. Other industry bodies such as API and DNV also publish important riser design codes. The international design codes are usually supplemented by the operator's own more detailed guidance, which account for previous experience and can often contain more stringent requirements than the standard design codes. I will now quickly talk through the various loads acting on the riser system and how these are considered in riser design. Firstly, the riser is subject to drag loading along the length due to currents. The current speed and direction varies with both time and elevation, and will have characteristics that are specific to location, season, and water depth. Maximum current speeds at the surface of up to 1.5 meters per second are not uncommon, and drilling has been attempted in surface currents of up to 3 meters per second. When we consider the combined effects of more than one parameter, it gets more complicated. Here, we are considering the effect of lateral motion of the vessel or vessel offset, in addition to current. The current causes curvature of the riser. In this schematic, the maximum displacement is shown as being at approximately mid-depth, although this will actually vary depending on the current profile. But the vessel offset is also causing the upper part of the riser to move away from the well location, which is fixed. In this schematic, the circles represent the upper and lower flex joints, and the colours represent the amount of rotation that is seen at each flex joint. Only a small rotation is allowed, typically only 2 degrees when drilling and less than 10 degrees at all times. Green indicates little or no rotation, and red indicates a large rotation. Yellow shows somewhere in between. It is shown that, for the same current, the vessel offset changes which part of the riser experiences the critical loading. With upstream offset, there is large rotation at the upper flex joint, but the riser displacement due to current means there is little rotation at the lower flex joint. With downstream offset, this scenario is reversed, and the riser displacement due to current means there is little rotation at the upper flex joint, but there are large rotations at the lower flex joint due to the vessel offset. Hence, it is important to assess these parameters in combination. This is fine when you are considering a single riser, but what about when there are multiple risers in close proximity? In this scenario, hydrodynamic loading on the downstream riser is influenced by the wake field generated by the upstream riser. The shielding effect of the upstream riser reduces the drag force acting on the downstream riser. But this is a complex phenomenon. If the two risers are not directly aligned with the current, then wake shielding may not occur. Additionally, lift forces due to velocity gradients in the wake field must be considered. Ultimately, it is important to design the system such that there is no contact between adjacent structures. This can influence the field layout, and options available include fine-tuning the positions of riser duties with different diameters and fluid densities, and adjusting top tensions to affect the riser response. Things get more complicated when wave loading is considered. Waves also have characteristics specific to location, season, and water depth. Wave motion will cause the vessel to move in 6 degrees of freedom, 3 axial and 3 rotational directions. This motion, together with the resulting hydrodynamic loading, transfers into the top of the riser. Each vessel has a characteristic response to wave loading, which defines the amount of motion in each degree of freedom for a given wave direction, height, and period. This response is known as a response amplitude operator, or RAO. This information is derived from simulations and model tests of the vessel, and allows us to perform numerical simulations where we define a range of wave conditions and the corresponding vessel response is modelled. Wave modelling can be simplified by considering a regular wave, in effect sinusoidal loading. However, an irregular wave is more realistic and should typically be considered in analysis. Various spectral models exist, which allow long-duration simulations to be performed that include a range of wave heights and periods. Both extreme and fatigue loading must be considered. During storm conditions, equipment limits must not be exceeded. Equally important is the build-up of fatigue damage over time from cyclical wave loading. The wave behavior at a given location is highly variable. To address this, wave scatter diagrams are generated for use in fatigue analysis. These diagrams, such as the example shown here, define the relative probability of occurrence of a number of individual sea states, where each sea state is a particular combination of wave height and period. In the diagram shown, HS corresponds to the significant wave height, a statistical measure equivalent to the estimate that would be made by a visual observer at sea, and TP corresponds to the peak wave period. We can simulate the riser response to each sea state with use of the vessel RAO plots as shown on the previous slide, and can therefore determine total fatigue damage by evaluating the damage associated with each individual or group of sea states, and factoring by the probability of occurrence. A deepwater riser may weigh hundreds of tons, and hence some form of tension or upthrust must be applied to prevent the riser buckling. Increasing the tension can also improve the riser response, with reduced fatigue damage and smaller flex joint rotations. Buoyant joints can be used in combination with or instead of top tension. Buoyant joints reduce the submerged weight and change the tension distribution along the length of the riser, but also result in increased hydrodynamic drag. Increasing the top tension does have a number of potential limitations, not least that it is important not to pull the riser out of a well. Additionally, with high axial stresses in the riser pipe, this reduces the capacity for bending and hoop stresses resulting from riser displacement and internal pressure. The top tension that can be applied is limited by the capacity of the tensioner system, and by the additional deck structure that may be required for the vessel to withstand the reaction loads. It is also necessary to design for system redundancy, so that a safe tension can be maintained in the event of partial failure of the tensioning system. The optimal riser tension will enable a safe riser disconnect by providing a positive tension at the base of the riser and a negative tension at the wellhead connector. As I have shown on the past few slides, there are a number of considerations when evaluating the riser response. These can be combined into an operating envelope, such as the example shown here, which shows the combination of vessel offset and current conditions under which a drilling riser can be operated safely at a particular location. The colours denote different operating conditions. In the green region, drilling can occur, while in the yellow region, the riser can remain safely connected, but drilling activity is not permitted. The non-uniform shape of the operating envelope is indicative of the fact that the riser response is limited by different parameters under different conditions. A riser may experience many years of cyclical environmental loading, and hence it will not be a surprise to learn that fatigue is a critical design consideration. First-order fatigue is caused directly by vessel motions due to wave loading. This is sometimes referred to as wave-induced fatigue. Second-order fatigue is caused by low-frequency motions, such as long-period vessel drift. Second-order fatigue is typically orders of magnitude less severe than first-order fatigue, but can still be important when evaluating the accumulation of fatigue damage. The locations of welds and geometry changes are particularly vulnerable to fatigue damage. Despite the large size of these structures, motions of just fractions of a millimeter can cause components failure in service if not accounted for correctly at the design stage, and I have seen examples of this happening. Another important source of riser fatigue damage is vortex-induced vibration, or VIV. VIV is caused by cross-flow of fluid across a cylindrical cross-section, such as a riser pipe, as can be seen in this video. Vortices form as the fluid flow separates downstream of the pipe. These vortices create low pressure areas, leading to lateral displacement of the pipe perpendicular to the direction of current flow. This causes lateral vibrations of the riser. These are relatively high-frequency cyclical motions, which can cause fatigue damage and lead to rapid failure of the riser. The extent of the IV excitation typically gets more severe with increasing current. The effects are particularly significant if the riser vibrations correspond to modal frequencies of the structure. Hence, the riser system can be tuned when necessary to change the modal response, for example, by changing the tension distribution along the riser length. Suppression devices can be installed in critical regions of the riser to disrupt the formation of vortices. An example is shown in the image on the left. It is also important to consider the drag amplification effect. If a riser is experiencing VIV, the lateral motions can result in increased hydrodynamic loading on the riser. This, in turn, can increase the wake shielding effects on any downstream risers, something that is particularly important when ensuring that clearance is maintained between adjacent structures. A number of software tools are available to support us when performing riser analysis. Local component analysis can use standard finite element software packages such as ANSYS and Abacus. However, global riser analysis typically requires specialist tools. Software such as FlexCom and OrcaFlex is optimized for the analysis of slender pipe structures with complex hydrodynamic loading. A global riser model will typically include the riser structure, hydrodynamic effects from current and waves, vessel motion response, and nonlinear stiffness from the seabed. I am often asked if riser analysis involves much CFD, due to the criticality of hydrodynamic loading. The answer, perhaps surprisingly, is no. In most cases, our fluid dynamics problem is fairly straightforward and is limited to fluid flow across the cross-section of a circular pipe. This behavior is built into the specialist software packages I just mentioned. The story does not stop once the engineering design is complete and the riser is installed. The next step is riser integrity management, which I can only talk about briefly today. Integrity management includes both inspection and monitoring. Inspections are performed at regular intervals and inform on the static condition of the system. Divers can be used, although remote inspections are now increasingly preferred. Visual inspections are used to confirm if the structure and local environment appear as expected. Ultrasonic testing can be performed to determine pipe wall thickness. Monitoring uses permanently installed sensors to inform on the dynamic response of the system and compare with the expected behavior. Typical data recorded includes position, strain, and acceleration. The measured data is stored and retrieved periodically, although real-time data transfer by cable or acoustics is also possible. Ultimately, the in-service data can be combined with the design data in a digital twin of the system to fully understand the riser behavior. Examples of this technology are currently being developed by various interested parties. As we near the end of this presentation, I want to briefly share with you a couple of interesting projects. Firstly, BP's Quad 204 development. This is a multi-billion-pound redevelopment of the Schiehallion and Loyal fields that were first developed in the mid-90s. The location is 175 kilometres west of the Shetland Islands, in 300 to 550 metres water depth. The original development produced nearly 400 million barrels of oil in 15 years, and technological advances should enable a further 450 million barrels to be produced, extending the field life to at least 2035. The redevelopment comprised the drilling of 8 new development wells and the installation of 21 new subsea risers. The start of production from the new field was announced in May 2017. My second example is a little less close to home and shows a structure installed by Petrobras offshore Brazil. This project used a novel design known as the BSR, with 4 large submerged buoys, each weighing around 2,800 tons and installed at 250 meters below sea level. Each buoy can support up to 23 steel catenary risers in a water depth of 2,100 meters water at 300 kilometers from shore. This is a unique project, but illustrates the vast scale under which such projects can be performed. To finish today's presentation, I'd like to look towards the future and a possible evolution in riser design. Composite materials are seeing growing consideration for riser applications as an alternative to traditional materials. Composites offer a range of benefits which could be utilized in an offshore riser application. These include lightweight, high strength, good fatigue resistance, and high corrosion resistance. It is not expected that composite risers will fully replace steel risers. However, in certain applications, there may be a particular characteristic of a composite pipe which means they are better able to meet the design requirements than a conventional solution. Airborne Oil and Gas and Magma Global lead the way in the development of this new technology, which is slowly gaining acceptance with various operators. However, there remains various challenges to be overcome, notably the product cost and the limited track record. This could be the subject of another presentation. And that's the end. Thank you very much for listening, and I look forward to taking your questions.
Well, thank you, Glenn, for an excellent presentation. We have a number of questions have come in, and as often happens, some of them have kind of grouped themselves together. So I'll try and sort them into groups and ask them together when I can. To start with, thinking about vibrations, you talked about external VIV, and there's one question about have you come across internal excitation due to dry gas or other flow inside the riser? Do you consider that when managing fatigue, and what approach and solutions do you have?
Okay, yes. Yes, so that's a different type of excitation, which I haven't discussed in the presentation, but it does occur. It's quite specific to a rough bore flexible pipe. So the corrugated metal carcass on the inside of the pipe, as dry gas flows across it, it will shed vortices which can cause excitation, which is known as flip or flow-induced pulsation. Now, the reason I didn't talk about that specifically in this presentation is the damage that causes, although a concern, it doesn't actually affect the riser pipe itself, but you have the excitation in the riser pipe, and then it will typically cause that damage elsewhere, so things such as the topsides pipe work. In terms of what you can do to manage that, you will try and design it out first of all. So you will try and set your process conditions, your flow rate, and your system design such that it's not vulnerable to this kind of excitation. Generally, any kind of excitation is bad, and you want to avoid that wherever possible. It's also worth noting that the guidance itself here is reasonably conservative. So this is something that we're looking at currently and trying to gather more field data to try and make the predictions more realistic and less onerous. But in terms of system opportunities to design it out, I know that there are different types of carcass under development, for example, which should be less vulnerable to that excitation.
Okay, thank you. Moving on, there was a question about the design life of the riser and how do you define the design life of the riser and associated components?
Okay, I don't know if it was just me, but your audio was breaking up there a bit, John. But I think I got the question that you asked about design life of the system and how it's defined. So the design life will it will be an operator requirement based on how they have estimated the reserves at a particular location and how long they want their system to last for. So in simple terms, if you imagine that they estimate how big the pot of oil is under the ground and how long it will take them to extract it, you want to make sure that your system doesn't fail before you've got all of the recoverable reserves out of that pot. So that will define the design life, usually with a healthy margin on top of that. And then what we do in the design is we try and make sure that we meet both the operational life, but also any other stages that part of the system will go through, such as installation, and with suitable safety factors on top of that as well.
Okay, thanks. And I hope you can hear me better this time. There was a follow-up question, which is, if towards the end of the design life, the asset owner wants to extend the life of the riser, how would you go about it, and are there techniques or analyses that you need to do to enable that?
I'm sorry, John, it's very difficult to understand you. I don't know if it's just me.
I'll try one more time, then I'll try a different way of connecting. Yeah. What options are there if the asset owner wants to extend the life of the riser beyond the original design life? How would you go about that?
Okay, it seems that I've got a bit of an audio problem because I can't hear John clearly, but I understand that other people can. What I'll do, John, because I can see the questions as well, if you just put a note in the chat as to which question you want to ask next, and then if you ask it, I can hear you talking, but I can't hear what you're saying, and I'll then give an answer. In the meantime, if I just pick one of the questions, and it might even be the one you've just asked, I don't know. So there's a question about what opportunities there are to use data analytics as part of the monitoring of in-service risers. So I'll tackle that question for now. Now, there's lots of potential here, and this is definitely a growing area. So when we perform the riser design, it's really based on a mixture of assumed and modeled or simulated information, but we don't actually know the actual system response. And that's because what will actually happen in service is there may be different environmental responses. So, for example, you might get a particularly severe storm comes through that hasn't been predicted, and therefore, if we use monitoring to record actual data, that tells us what's actually happening, but it's often still in a raw form. So we still need to process that data to understand what it means in terms of how the riser itself behaves. And where data analytics is really going to help is it should allow us to build this model, such as something like a digital twin. There's various forms of that, whereby we can learn from the actual system response and predict what that means in terms of the riser behavior under different combinations of conditions. So effectively, we're updating the model built in design and making it more closely reflect the actual system behavior. And that in turn should help us to either set clear alarms for unsafe conditions, or alternatively to allow safe life extensions.
Thanks. Okay, the next question will we still need subsea risers in a world that's moving away from traditional resources such as oil and gas?
Okay, yes. I think the short answer to that is yes. Now, obviously, I would say that because if not, then I'm out of a job. But the reason that I think that subsea risers are still important, first of all, subsea oil and gas is unlikely to disappear completely from the energy mix anytime soon. There will still be some requirement for risers. It might be reduced from the present day, but there will still be something. And it's going to get more complex. The ways in which risers are designed and installed is going to face increasing cost pressures and demand for sustainability in terms of how we approach this. And we've recovered the reserves from all the easy places. So any new fields that we go into, they're quite likely to be in ever more challenging environments, ultra deep water, more severe environmental conditions, for example. So we're going to need to keep on evolving the technology to meet these sort of developing challenges. And I'd also add that it's not just for recovering oil and gas either. So one developing area is carbon capture and storage. And one of the concepts that's being considered for that is using subsea reservoirs and injecting carbon dioxide in subsea. So that would be using a riser to do that.
Okay, thanks. So the next question, I think to some extent you answered this towards the end of the presentation, but just to clarify, how many of the pipe designs require detailed stress analysis, and how do you decide what does and what doesn't require that analysis?
Okay, so I think it depends what exactly is meant by detailed analysis. I mean, the short answer is that all of these riser pipes will be assessed to confirm that they have an acceptable behaviour. Now some of that will be done just with hand calcs. So, for example, if you're trying to define your pipe size requirements, so your wall thickness, for example, that can be a hand calc based on the pressure requirements. But when we get into the dynamic behavior, that is when you would probably need to actually build a finite element model in order to capture that response. There are some shortcuts that can be taken. So if you had a field with a number of similar risers, you might be able to identify the most critical one and focus your detailed analysis on that case. And I know that for some shallow water systems, and particularly in the North Sea, where there's a lot of history, there have been some attempts at producing a standardized approach where you can really simplify the amount of assessment that is performed by using that knowledge and experience that has been gained from previous projects to try and almost predict a standard response to a standard system. But the nature of these systems is such that generally there are typically unique requirements for each system, and quite often you would revert back to the detailed analysis.
Thanks. The next question is about steel catenary risers compared with flexible risers. What are the key considerations in making that choice? What factors would you look at?
Yeah, not a simple answer to this question. There's various pros and cons of the different types of system. So if I just try and pick out a couple of examples to illustrate the point, a flexible pipe will typically have an improved fatigue response. compared to a steel pipe. If you think of the construction of that flexible pipe, it's more compliant and it's easier to bend, so it's not going to be quite as susceptible to that dynamic loading. So that's an advantage. But on the downside, it's because it's more complex, the potential failure scenarios that you've got to consider are more complex, and it's also more costly and can be provided by fewer suppliers. There will also be some preference on behalf of the individual operators based on what they might have track records in operating and therefore managing in service. So it's typically something that would be looked at in the early stages of the design process. There'll be a concept evaluation that will weigh up the pros and cons of different systems.
Okay, thanks. Now, I guess another multi-part question. When riser failures occur, how do they get repaired? Do you have to replace the entire length due to the top tensioning, or can it be done in sections? And I guess a related question is, if you discover a leak during operations, what can be done to repair the leak?
Yeah, so the first thing to say is that any kind of riser failure or even a leak is something that we really don't want to happen. There's sort of quite serious safety and environmental implications if it does occur. So we're always trying to do as much as possible in the design phase to make sure that doesn't happen. Now, things do happen in service, and you can get some kind of damage, which maybe results in a small leak in different parts of the system. It is quite unusual. I don't want it to sound like this is an everyday occurrence. But the options available, it really depends on where it happens. So if it's in the sort of specific parts of the structure or equipment, then you might address that in a slightly different way to the pipe. With regard to the pipe itself, there are options available to fit an external clamp or sleeve in some situations, which will help to seal the offending region, but it's certainly not suitable for every application. And you're looking at it more generally. One of the big challenges with risers is that you can't just replace part of the system. So if you imagine a pipeline, even the pipelines that you get on the seabed transporting oil and gas, it is theoretically possible to seal the pipe and cut out a section of it and replace it. If you've got a vertical riser, you can't take away the middle bit and replace it. You have to replace the whole lot.
Thanks. And there was a question about your view on the corrosion challenges for subsea risers.
Yeah, it's so we've got both potentially both internal and external corrosion to worry about. So it's definitely an important part of the design considerations. In terms of internal corrosion, that will be affected by whatever the bore fluid is. So depending on what reservoir you are producing the oil and gas from, there may be different chemical compositions, and that can lead to different types of corrosion. What we can do about it, a few different options. Crudely, we can make sure that we have sufficient thickness to accommodate any material loss, and we can use cathodic protection to protect the system. But also, where greater level of protection is required, we can use things such as a corrosion-resistant alloy to clad the pipe. Also, I know it's one of the perceived advantages of composite risers is that they are more corrosion resistant, and therefore when you have a highly corrosive environment, that may be a potential application for the composite systems.
Great, thanks. And we're pretty much at time, but one final question, because there have been a lot of questions come in. What designs are being utilized to overcome temperature differences in deep risers from subsea to surface and obviously within the pipe? And do you have any examples of deep risers operating in extreme cold climates? And if so, how do those challenges get overcome?
Okay, I mean, looking at the subsea part, there is much less variation in temperature than there is in the surface part. So it will usually be the top part of the riser that actually sort of comes out of the water and up to the rig. That's where we will see the greatest temperature variation. What you can do about that, it sort of, for example, you might want to put some kind of a shield in place to protect the pipe from the worst of the sun in a very hot location. In terms of cold locations, there are things you can do with external insulation. That in itself then becomes something else that you have to make sure you manage the integrity over the field life. So a covering that protects the riser in the short term will still have to last the whole design life to avoid getting problems later on.
Okay, thanks, Glenn. Thanks again for an excellent presentation, and thanks for answering all of those questions. Thanks to everybody who listened in, and a special thanks to those of you who submitted questions. I'm sorry there wasn't time to get through all of them, but we did as many as we could, and hopefully we've got a good cross-section. It just now remains to me to thank you all for attending, thank the IMechE for putting this on, and to formally bring a close to the event. So goodbye, everybody.